Good day. Today I will be discussing with you another topic in machine elements. But before that, let us have a quick review on our previous topic, which is instantaneous center. In that topic, we defined what are the instantaneous center, what are the different types, how to compute the number of instantaneous center using a formula. We also discussed the Kennedy's rule and how we can use this in locating the instant centers. We also have there some examples for 4-bar slider crank and 6-bar linkage for us to understand how to locate the instantaneous center graphically. And also, we end that with applications of instantaneous center. This topic is very important in velocity analysis, but I hope that we will be able to apply everything that we learned from that topic in this new topic, which is velocity analysis. At the end of this lesson, you should be able to describe the importance of velocity analysis in the design of mechanism, compare the different methods of velocity analysis, combine the different semi-graphical methods of velocity analysis method to solve linear and angular velocities in linkages. Why is it necessary to determine the velocity? Once a position analysis is done, the next step is to determine the velocities of all links and points of interest in the mechanism. Once we establish that the mechanism will really move according to our different conditions that we establish, just like the Grashof condition, once we are certain of how the linkage will move, it is also important for us to determine the velocities of the different links and points. We need to determine the velocities in mechanism because it will help us to calculate the stored kinetic energy in that particular linkages using the formula 1/2 mass times velocity squared. It will also help us to determine the links acceleration that are needed for the dynamic force calculation using the formula force is equals to mass times acceleration. So once we determine the acceleration and the kinetic energy, it will be easier for us now to analyze the entire system in kinetics, not just in kinematics. So what is velocity? Velocity is defined as the rate of change of position with respect to time. I believe that we are already familiar with that. Velocity can either be angular or linear. Angular velocity will be denoted as the symbol omega and the linear velocity as v, where our angular velocity omega is equals to the time rate of change of its angular position, while the linear velocity is the time rate of change of its position. Since velocity is a vector, it always has its direction. So velocity is always in a direction perpendicular to the radius of rotation and tangent to the path of motion. So as you can see here in this illustration, the center of rotation is the point, the joint A here of this particular link. So the direction of the rotation is denoted by the symbol omega. As you can see here, if omega is moving in a clockwise direction, then the velocity will also move in that direction. For example, at point P, the velocity of point P will also be in the same direction, which is clockwise, and it is perpendicular to the radius of rotation. So the radius of rotation here is the RP. So the length of this link here. So this is the RP. So as you can see here, the velocity is perpendicular. So it makes a 90-degree with respect to the link. And it's also tangent to the path of the motion. So what is the difference between velocity difference and relative velocity? Velocity difference, we will use that for 2 points in the same body. But relative velocity is used for 2 points in different bodies. But they will have the same equation, which is V subscript PA. And that is equals to the velocity of P minus the velocity of A. So the velocity difference, or the relative velocity, is denoted by that equation. So to illustrate velocity difference, so we have here velocity of A and then the velocity of point P. So the velocity of A, since A is a slider crank, so it will move in this, it will be guided by this ground to move in this path here, as you can see. While the velocity of P relative to A is denoted by this perpendicular line here with respect to the angle of rotation. So the velocity, the relationship between them, the velocity difference is used when they are connected in the same body, as you can see here. So point A and point P are found on the same link. So they are, we will use the term velocity difference. So here, to resolve the different velocities, we can see that the velocity of P is just equals to the velocity of A plus the velocity of P relative to A. So the velocity of P, the absolute velocity of P, is equal to the velocity of A added with the velocity of P relative to A. So VPA now is the velocity difference between P and E. Relative velocity, on the other hand, is used when referring to different bodies, as you can points at different bodies. So we have here link A and link B. This link here, link A, this link has a velocity of A moving in the direction horizontal. And then we have here another link with point P. The velocity of P is moving in this direction denoted by this arrow here. So these 2 points are points on different bodies. Say this one is car 1, car 2, and then we have car 1. So the relative velocity is the difference actually with their velocities. As you can see here in this velocity diagram, if you're going to get the velocity difference for different bodies, the velocity of A now will be the negative of its actual velocity. So to get the relative velocity of P with respect to A for bodies on different, they are not on the same body, we will use the difference. So you can see here that the relative velocity is the difference. So Vp, the velocity of P, minus the velocity of A. So the velocity of A now is the negative of the velocity of A. So that is the relative velocity. Another important concept here that will help us is the velocity of rotating and oscillating cranks. The magnitude of instantaneous linear velocity of a point on a revolving body, a rotating crank or oscillating crank, is proportional to the distance of that point from the axis of rotation of the body or crank. So to illustrate, say for example you have this crank here. It's rotating as denoted by this counterclockwise by the direction of the angular velocity. Say for example you have 3 points A, B, and C, and we'd like to get the instantaneous linear velocity of these different points. So to get the direction and the magnitude of their velocities, the linear velocity, we'll first draw a line connecting them to the center. So as you can see here, that's the radius AO, radius BO, and radius CO as their distances from the common point or the axis of rotation. So the axis of rotation is this one. So A, B, and C is rotating with respect to this axis. So their linear velocity is, they are proportional to the distances of these different points to the axis of rotations. So as you can see here, since A is closer to the axis of rotation, its linear velocity is smaller as compared to B, which is farther away from the axis of rotation, while C has the greatest linear velocity since its distance is also it's also the one that is most distant from the axis of rotation. So this illustrates that the linear velocity is proportional to its distance from the axis of rotation, and they are perpendicular with respect to the line joining the axis of rotation and the point, as you can see here. Those are perpendicular. So to get that velocity, we will use the formula omega multiplied by its distance from the axis of rotation r. So omega is usually given, as you can see here, and the radius is you measure it from the axis of rotation to the point. And if you want to get the angular velocity, on the other hand, the angular velocity can be computed by rearranging this equation. As you can see here, for these 4 points rotating on the same body, on the same link, they will have the same angular velocity. So the angular velocity of A, B, and C is the same, but their linear velocity is different because that is dependent on their distances from the axis of rotation. So I hope that it's clear with us how to get the linear velocity and angular velocity of the points in a particular body. So let us try to make our calculation easier by defining some important concepts here. The space scale. So usually in our actual problem, the distances or the measurements are too big for us to draw them in the paper. So that's why we use scaling. So as you can see here, we can use a space scale such that, for example, you can represent 1 inch on drawing equals so many feet in actual. So for example, 1/4 feet in actual is 1 inch in your drawing. So that's what we meant by the space scale. You can also use centimeter. Say for example, 100 kilometer in actual is 1 inch or 1 cm in your paper. So in that way, you can draw it in your paper because 1 cm can be drawn in the paper. Then we also have velocity scale denoted by the symbol kV. So example, 1 inch in your drawing represents a particular feet per second or meter per second. So for example, if your kV is 1 inch, so that means that 1 inch in your paper is 5 feet per second in actual. Or 1 inch or 1 centimeter in your drawing represents 5 meters per second. So depending on the scale that you will use. Then we also have the acceleration scale. So it's almost similar to the velocity scale. Say for example, you have 100 feet per second. You can draw that in your paper as 1 inch in the drawing. So there are two methods in velocity analysis. We can do it analytically or graphically. Analytical methods are more complicated because this requires knowledge of equations that has to be resolved. That is why we will not use this method here. But we will use the graphical method because it is more direct, less complicated, and it's sufficiently accurate. Though in comparison, analytical method will be more accurate because you can really get the actual value. The good thing about analytical method is this has been used already in softwares and some simulation tools. But the knowledge on graphical method will help us to understand how these softwares are built. So the softwares, those are actually based also on the graphical methods. So there are 4 methods of velocity analysis, and these are the resolution and composition method, the instantaneous axis of velocity method, the Centro Method, and the relative velocity or velocity polygon method. So let us try to examine them, beginning with the resolution and composition method. So for the resolution and composition method, what's needed here is the velocity of one point in the linkage and also the direction of the velocity of any other point on the body. Once we can get the velocity of one point and the direction of the velocity of any other point, we can also get the absolute velocity of those unknown points. It can be done by resolving the known velocity vector into components. So that's why it's composition method, because we are going to resolve it into components along and perpendicular to the line joining the 2 points. And making one of the components of the velocity of the other point equal to the component along that line joining them. Say for example, you have here 2 points A and B. And you know the velocity of A. So to get the velocity of B, it's important that we know the direction of the velocity of B. Say for example that you know that the direction of B is in this line here. So B will move in that line. So our purpose, our goal is to get the velocity of B, the direction of the velocity as well as the magnitude. So the magnitude of A here is actually predetermined. Say for example, you determine that the velocity of A is 100 meter per second, and then you use 1 inch is 100 meter per second. So say this is 1 inch. So you just draw it here. So that's how you you use the velocity scale. So according to the method 1, which is our resolution and composition method, we're going to resolve A into components along and perpendicular to the line joining them. So the line joining A and B is this line here. So we're going to resolve this velocity into this line, horizontal and perpendicular to this line, and these are the 2 points. As you can see here, we have an arrow here that is along the line, and then we have another arrow here which is perpendicular. So we basically get the components of A, the velocity of A. So these are the 2 components, along and perpendicular to the line joining A and B. And then we're going to measure this this line, and then we're going to place that in the line at point B, because this same line here is this component here is also the same velocity that is acting at point B in this line of action. So that's why we draw it here in the line connecting them, this component. And also once we get since this vertical component is not directly related to B because they are not connected on that line, so we are just concerned with the component that is located in the line joining them, and that is this component. The perpendicular one is not related at all. So that's why we will use this, and then we're going to resolve this into the component wherein we can get the velocity of B by drawing a perpendicular line to that in the direction of motion, as you can see here. So since the direction of motion of B is this one, we know that the absolute velocity of B will always be in this direction. So if we draw a perpendicular line, then by the knowledge of head to tail, diba, we added the second vector to the head, the tail of the head of the first. Then the sum would be the line that will join them would be the line that would join the tail of the first vector to the head of the second vector would be the absolute velocity. So by the knowledge of vector. So if we draw that, so we can get if we connect that, then we can get the absolute velocity of B. So here, we were able to get the absolute velocity of B. So by using the resolution and composition method. So that is if we have 2 points connected on the same line. So what if we have 3 points? So we have 3 points, and then we wanted to get the velocity of points B and C if the velocity of A is given. Say for example, the velocity of A is known in this direction. And we wanted to get what would be the velocity of C and B when the velocity of A is in that direction. So in order to get the velocity of B and C, first we will use the method that we already know. We're going to resolve the velocity of A into two components parallel and perpendicular to the line joining A to both B and C. So let us start first with the line joining A and B. So the line joining A and B is this line here. And then the component of A perpendicular to that line is this one. And the line that is along is this one. So as you can see here, we resolved it in B. So the direction should also be the same because the direction of A now is towards the left. So the direction of that component with regard to point B should also be to the left. So that's why we have it here to the left along the line joining them. If we already know that the direction of B is along this line, say for example that we know that it is given in the problem that the B is known to move in this direction, then we can get its absolute velocity by drawing a line from its head, connecting it to the direction, and using head to tail, we know that the third side would be the absolute velocity. So the velocity of B would be in this direction. So this means that if A moves in that direction, point B will move in this direction here. So this is important in mechanism, right? Because we wanted to predict the behavior of the different points when this particular joint is in this position, what would be the position of the other points. So basically that's what we are doing in here. So now that we know the absolute velocity of B, we would like to get also the absolute velocity of C. So it's important that we will solve first the point where we know the direction of its motion. So do not solve yet the point that we do not know yet its direction. So always focus on the points that we know the direction, because as you can see here, for A we know its absolute velocity, we also know its direction. But for point B we do not know yet its absolute velocity, but we know the direction. That's why we solve it next to A. So for C, we'll use this data now to get the absolute velocity of C. So first we're going to resolve again the absolute velocity of B to two components. So one that is perpendicular and along the line joining them with C. So as you can see here, this line here, this line BC connects B to C. So the line that is perpendicular to that, the component of B, the component of VB, or the velocity of B, is this line here, this red line. This is perpendicular. It's not perfectly perpendicular in the drawing, but it should be perpendicular. So this line, assuming that it's perpendicular, then we can get the third side. This is one. So the line that is along B and C. So that is the VB is equals to CC1, as you can see here. So this line here, VB is equals to CC1. So this is the component of B, the absolute velocity of B, that is equals to the component of the absolute velocity of C with regards to this line. And then we will also resolve the velocity of A with regards to the line joining A and C. So as you can see here, this line join A and C, and we draw a perpendicular line of A, the absolute velocity of A to that line, and then we get the component along. So this is the component along, and also the direction. Since the direction of A is in that, so obviously A should be moving in this direction. For B here, since B is moving in this direction, obviously it should move in that direction, so that when you add this one and this component, it will be moving in that direction. So now that we know that two components of C, which is CC1 and CC, then now we can get the absolute velocity by using the parallelogram method of vector addition. Diba? If we add them tail to tail or head to head, we will use the parallelogram method. So we draw parallel lines to CC and CC1, and then we connect its point to the intersection, and that is a C2, and that's where we can get the velocity of C. So that is the absolute velocity of C now. So as you can see, we can also get the other points if we just know the direction and the velocity of one point or 2 points in the linkage. So let us try to apply all those concepts in solving this problem. So here we are given with the linear velocity of A represented by this line, AA1 or AA. So we are to determine the linear velocity of D. So this is point D. As you can see here, point D is a slider crank mechanism. So it's constrained to move in this direction, while point B is also a slider. It is constrained to move also in this direction. So this line here, AC, can be considered as a floating link. So it will just depend where the point A and C would move. So here the velocity of A is known, and we also know its direction. So the direction is based on this arrow here, it's towards this direction. And we wanted to get the velocity of D when A is moving in that direction at this particular position. So applying the principles that we already know, we're going to resolve the velocity of A into the components joining the point to the other points that we wanted to get its velocity. Since B is a slider, it's obvious that its direction will always be in this line. So this means that we know the direction of B. We are sure that it will move whether to the left or to the right in this line. So we will use that direction to get its absolute velocity by using this component here, AA1. So we resolve that component into the points that we'd like to get its velocity. So we resolved it because this is the line joining A, B, and C. That's why we draw the same. We measure AA1 and then we draw it here. And then the direction should also be the same. And since we know that the direction of B is in this direction or that direction, we're just going to draw an arrow that will connect it. So this is the arrow that is perpendicular to the head of BB1. So as you can see here, BB1, and then we have an arrow. So therefore, we can get the velocity of B, obviously, by connecting the tail to the head of the last vector or the last arrow. So this is the direction, therefore, of point B. So this is B, B, and this is our absolute velocity of point B. So now that we know the absolute velocity of B, we will use this velocity as well as the velocity of A to get the velocity of C. So another strategy that will help us, so if we have 3 points and they are on the same line, we can actually get the velocities of the other points by using proportion. What we're going to do is we're going to connect the velocity, the head of the velocity of A to the head of the velocity of B. And then we will use that to get the velocity of C. So if we connect that, so you can see here that we connect the head of A and the head of the absolute velocity of B. And then the velocity of B is a line that will connect C to this same line because they are on the same point of rotation. So if we're going to resolve now, since we know that one of the component of C is known, so we know that this is the component here, CC1, we're going to draw a line perpendicular to the head of CC1. And this is this line. So the intersection of that line to this proportional line that's connecting the head of AB is the absolute velocity of C. So we're going to draw an arrow from point C to this intersection. And that is now our velocity of C. So in this method, we were able to obtain the velocity of C. So that is one technique that we can use if there are 3 points in the same line. So we can use the proportion. And now that we know the velocity of C, and since C is connected to D, we can use that to get the velocity of D. So we resolve C again into components along and perpendicular to the line joining C and D. So this is the line joining C and D. And then the component that is perpendicular is this one. and then the along is this one. So we just draw it and then we transfer it to D. So that's why we have here DD1 is equals to CC2. And then finally, we're going to, since we know that the direction of D is in this line here, since it is constrained to move in that line, we're going to resolve it. We're going to connect DD1. We're going to draw a perpendicular line to that head to this line. So we draw a perpendicular line. So take note that the 90 degree should be from the head. So this one is the 90 degree here is this one, this connection. And then the velocity of D would be the intersection. So that is the absolute velocity of D now. So as you can see, if point A will move in that direction in a link, point B will move to the left, point C will move to that direction, and point D will move downward. And we can also get the magnitude if we know the scale. So for example, the velocity of A is 1 inch is equals to 100 feet per second. So you measure this one, and then you get the equivalent feet per second. And then you also measure this one, and you get the equivalent feet per second using the velocity scale. So that is how we get the magnitude and direction of the velocities using the first method, which is the resolution and composition method. So now that we know the first method, let us try to examine and compare it with the second method, which is the instantaneous axis of velocity method. So for the instantaneous axis of velocity method, it's important for us to note that there is one instantaneous axis for each floating link in a machine. So that means that we can use this instantaneous axis to get the velocity of these different points. Because if we say instantaneous axis of rotation, the different points will now rotate in the same angular velocity with respect to this instantaneous axis. So there is not one common instantaneous axis of velocity for all links in the machine. That is why it's important for us also to know, to get first the different instantaneous center. So if we use the different, we can use the different instantaneous center to get the velocity for each link. The instantaneous axis of velocity changes position as the links move. So since in actual practice, links will really move, then the instantaneous axis will also move. And also the velocity also moves or changes as the links move, which is very obvious. Say for example, we have the same problem as before. So as you can see, this is the same problem as method number 1. And we're given with the linear velocity of A, which is represented by this one again. And we wanted to get the velocity of D. So the same problem, but we will use different method. So for the instantaneous axis method, we're going to get first the centro. So using your knowledge in centro, or your knowledge in instantaneous, locating the instantaneous center or the instantaneous axis of rotation, you're going to get, or you're going to determine which instantaneous center you will use. So for this problem, we will use the instantaneous center that's connecting A and C. As you can see here, this is the instant center locating, connecting A and C. Because if we get this value, we can also get D because they are connected. So we just bypass B. So that's the good thing about the instantaneous axis method, because you can directly use the center as long as they are connected. As you can see here, since A and C is connected, they are on the same link, then, which is link 3, right? So this is link 3. A, B, and C are link 3, are in points in link 3. So these 3 points now will have the same angular velocity with respect to this instantaneous axis. So how do we get Q3? Again, you can get that using your knowledge in topic number 4, which is the IC. So the locating of the instantaneous axis of rotation. So this is already determined, that's why we have it here, Q3. So we use this instantaneous center. There are many instantaneous center for this because this is composed of different links. But we use this because it connects A and C. So using this instantaneous center, we are going to draw a circle that will end to the velocity of to the point A. So this is the circle. So as you can see, this circle, the radius of this circle is AQ3. So you're going to draw using compass Q3A, and then you get that radius, and then you're going to create a circle. So with the center now is Q3, the radius is Q3A. So the rationale is that because the velocity of A is known. So since the velocity of A is known, we're going to get we're going to create a circle based on the radius connecting A and Q3. And then we're going to swing. So we swing this velocity A here to the line joining Q3 and C. So the length of this arrow, so the magnitude of this arrow here is the same as this one. So we just swing it, so along the circle, no, to the line connecting Q3 and C. So this is the line connecting Q3 and C. So we swing it, and then since we know that they will have relationship in terms of angular velocity or angular linear velocity. So the angular velocity of the points now would be the same, but they are dependent on the distances. So therefore, we can use ratio and proportion to get the velocity of C. So how to do that? We connect Q3 to the head of A, this apparent A here. So to the head. So this is the line now. And then we're going to get the velocity of C, since we know that the velocity of C should be perpendicular to this line, just like A, diba? Because with respect to the center of rotation, all the velocities are perpendicular, right? And it is proportional to the distances to the center. So this is just a virtual center, but all of these points now have a relationship to that instant center. So we're going to draw also a line that is perpendicular to this Q3C, and that will intersect to this line here, so that it will be proportional. So as we draw that, that is actually now the absolute velocity of C. So as you can see, this is the same that we get from the method 1. So using method 1, we got the same result as the method 2. It's just that we have different method. So now that we have the velocity of C, since D is connected to C, so now C and D are points on the same link, which is link 4. So C and D are on the same link 4, meaning they will have relationship in terms of the angular velocity in their common center. So we need to get the common center of C and D. So using again your knowledge on topic 4, you determine that there is an IC here connecting C and D. So there is a triangle again here connecting C, D, and this IC, Q4. So using this IC, we're going to use again another circle which has the radius of Q4C, since C is known. So we draw a circle with radius Q4C. So this is the circle. So again, it's not really very perfectly located now, but this is the radius of this orange circle is Q4C. So we swing again VC, just like what we did before. We swing it to the line joining Q4 and D. So we swing it there along rin gihapon no sa ato ang orange circle. And we will use that to get the absolute velocity of D. So since we know that the direction of D is in this line, then if we connect Q4 to this head here, so we connect it. So Q4 and then the head. So this Q4 is an IC. It's an instantaneous center. So we connect it, and then since we know that the direction of D is in this direction, it's obvious to us now that the velocity of D would be the intersection. So this is the velocity of d. As you can see, it's proportional. So velocity of c is uh, longer or greater because it's farther away compared to the d with respect to the instantaneous center. So as you can see, we get the same result for the velocity of d, which is moving downward, if we have the velocity of a using the same method. So if you want to get the velocity of d, then you also have, so you will just use actually the same center here because this q3 is also the instant center of this point d here. So that is the method number 2, which is the using the instantaneous center to locate the absolute velocity of other points. So as you can see, the only challenge with this method is to determine first the instantaneous center, and then the rest will be very easy. The good thing also about this method is that it's very flexible and we can use it to various kind of linkages as compared to the first method. So the question here is actually to get not just the linear velocity of d, so this is the linear velocity of d, but also the angular velocity of link 4. So to get the angular velocity of link 4, so this is the link 4, so this line BC is the link 4. If you want to get the angular velocity, we will use the formula. The angular velocity of 4 is the velocity of d divided velocity of c, the absolute velocity of c, this one, divided by the distance q4c. Similarly, we can get that using d also. So that's the velocity of d divided by the line connecting q4 and d. So that is how you get the unknown, which is the angular velocity of link 4. The same also if you wanted to get the angular velocity of link 3. So that's the one of the advantage of using IC, because you can, it's, if you want to get the angular velocity, since you already know the distances from its center of rotation, then you can use that to get the angular velocity of floating links, just like DC and AC here in this problem. So as you can see, this method is kind of challenging, but it's more convenient if you are more familiar with the instantaneous center, of locating the instantaneous center. So now that we know the two methods, the third method is the Centro Method. It is somehow similar to the instantaneous axis of velocity method. The good thing about Centro Method is that we can use some analytical first and then use the instant center. So it's a combination actually. So the Centro Method, the rationale about this method is that the instantaneous angular velocity of two links are inversely as the distance from their common centro to the center about which they are turning or tending to turn. So we will illustrate this statement later on in solving the problem. So for example, you have here a problem. We have a pin-jointed 4-bar mechanism. So we have a pin-jointed 4-bar mechanism wherein the length of AB is 300 millimeter, BC is 360, also the same with CD, 360 millimeter, and AD is 600 millimeter. The angle BAD, so this angle here is 60 degrees. So if this angle is 60 degrees, the crank AB rotates uniformly at 100 RPM clockwise. So this means that this link AB here, so this is a crank. So if you use Grashof condition, you can verify that this is a crank. So this crank rotates uniformly at 100 revolution per minute clockwise. So the clockwise direction is in that direction. So you have a clockwise direction, so it's rotating clockwise at 100 RPM. So you're going to locate all the instantaneous centers and find the angular velocity of the link BC in this position. So if the position is this one, 60 degrees, if the position of this crank is at 60 degrees with respect to the ground, what would be the instantaneous centers, including the virtual instantaneous centers, and also find the angular velocity of link BC. So we wanted to get omega BC, or the angular velocity of link BC. So using the Centro Method, so first we are given with the rotation of AB, which is 100 revolution per minute. So the next step is to get the angular velocity of AB. So the angular velocity of AB can be computed using the formula 2 pi n. So 2 pi n. So that's 2 pi multiplied by the revolution per minute. So that is 100 revolution per minute. So that's 2 pi multiplied by n. And since it is in minute, we will convert it to second by using the conversion. 1 minute is 60 seconds. That's why we have the angular velocity of AB in rad per second is now 10.472 rad per second. So you may be wondering why is it now rad and not rev? Because the 2 pi here is the conversion factor between rev and rad. Because we know that 1 revolution is 2 pi rad. So that's why rev will be cancelled out because 2 pi divided by rad. So rev will be cancelled out. So that's why we have here 10.472 rad per second. So that means that the angular velocity of AB is 10.472 radian per second. So now that we have the radian of AB, we can get now the velocity of B. So this, since point B is still connected, this is still on the same link, AB, then we can get its absolute velocity by using the formula. You multiply the angular velocity to the distance of point B. So from the axis of rotation. So we multiply the result that we have earlier to the distance AB. And since AB is 300 mm in meter, it's 0.3. Then the absolute velocity of point B, so it's the linear now. It's not angular, it's the linear. The linear velocity of B is 3.1416 meter per second. So now that we have the velocity of B that is 3.1416 meter per second, then you may use the velocity scale to draw it in the paper. So maybe you can let the kV as 1 inch in your drawing is 3.1416 meter per second. So that is the kV or the velocity scale. So that you can draw this in the drawing, in the paper. So, but before we do that, we will first use our knowledge on topic number 4 and get the ICs. So this is very familiar to us already. We know that the ICs are located here. For I24, we have I23, and then we have I3. So now that we have the ICs, we will use that. You also that URI for Centro because they have relationships. So the velocity of B using the Centro, the concept of Centro is also, aside from this one, aside from this definition, the velocity of B is also equals to the angular velocity of this link BC and the distance of this point B to this instantaneous center I3. Because basically, with respect to this instantaneous center, this 2, 3 to 3, 4, all of the points here connecting 2, 3 to 3, 4. So basically, all of the points in link 3 has the same angular velocity. And that is your angular velocity BC, which is the one that we are looking for, right? The angular velocity of link BC. So the velocity of B, so the velocity of point B, if you're going to base it in this IC center, is also equals to this angular velocity of BC and the length of the line joining that point B to the instant center. So that's why we have this formula here. So this is the formula that we will use to get the unknown. So we just we first use semi-graphical approach, or you can use ruler. No, you can use ruler. You measure the distance of this instant center 1, 3 to 2, 3, or you can use also trigonometry, whatever is easier. Because you can also use trigonometry because we have 60 degrees here. We know the degree here. Then we can get also the distances here. But the easiest is to use semi-graphical. So you just use a space scale first and then use a ruler to get the distance. So now that we have the distance 2, 3, and 1, 3, as well as the distance 1, 3, 3, 4 using a ruler or using trigonometry, we will use these distances, we substitute it in this formula. So we substituted, we know that the velocity of B is this one, 3.1416 meter per second. And then the distance I3B is 494.4 mm or 0.4944 meter. Then we can get the angular velocity of the link BC as 6.3 rad per second. So as you can see, you are able to get, so the angular velocity of the link BC is lower than the angular velocity of the link AB, which is 10.472 rad per second. So that is how you can use the Centro method for this case. So let us have another example. So you have here a slider crank mechanism. So we have a crank OB. So this is a crank OB and a connecting rod of length. The connecting rod AB. So this is a connecting rod, and this one is the crank. So the crank is 100 mm, and then the connecting rod is 400 mm. So if the crank rotates clockwise, signified by this arrow here, it rotates clockwise with an angular velocity of 10 rad per second, find the velocity of the slider A, so the velocity of the slider A, and the angular velocity of the connecting rod AB. So not just the linear velocity of A, but also the angular velocity of this connecting rod AB. So if that is the case of the problem, the best way is to use the Centro method. So first we will get the ICs. But first we will solve for the equivalent velocity of B. Since we know that OB is 10 rad per second, so this one is given in the problem. The angular velocity is 10 rad per second for this link. So it's 10 rad per second, it's constant now. All of these points has the same angular velocity. So point P will also have the same angular velocity, which is 10 rad per second. Then the velocity of point B, which is found in that same crank, would be the distance of point B from the center of rotation to the multiplied by the angular velocity. So we can get the absolute velocity of B, which is 1 meter per second. So what we're going to do next is to locate the instant centers. So using your knowledge again of the instant center locating of the instantaneous center, we got the instantaneous center here, I3 and I4 at infinity. We also have the I4 at infinity. And the other instantaneous centers are also shown already for this problem. And then we also already draw the velocity of B. So since it's rotating clockwise, the direction of B would also be the same. So that's why the arrow is moving in that direction, not on the opposite. So since we know that this crank is rotating clockwise, the velocity of B also is in that direction at 90 degrees by using the theory. So this is the velocity of B. So the length is depending on your velocity scale. So assuming that your 1 meter per second is 1 inch or 1 cm in your drawing, then you draw 1 cm here or 1 inch, depending on your velocity scale again. So now that we draw VB, we're going to use our knowledge that if they are located in the same instant center, they will have the same angular velocity. So therefore, the velocity, so this velocity of A over the instantaneous center, the distance of the instantaneous center I3A, so this one. So this is I3. So we focus our attention in this instantaneous center I3. The distance of this instantaneous center I3 to A, this one is I3A. So this is the I3A. And then the I3B is this one. So we use this instantaneous center because it connects A and B. So it will help us get easier the velocity of A later on. So again, we use this because it connects B and A. So meaning I3 is a common center of rotation for point A and point B. So if that is the case, that means that point A and point B will have the same angular velocity. with respect to this point. So again, A and B will have the same angular velocity with respect to the instantaneous center I3 because they are connected. So that's why we have this equation. So our VA over I3A is just equals to VB over I3B because that is equals to the omega, right? Or the angular velocity. And when we measure using ruler this distance from that instant center to the points, we determine that the distances are as shown. So you can see here the distances. So the distance I3A and I3B. So using these distances, we substitute it in the equation that we established. So substituting these values in the equation and also the velocity of B, which is already known, we can get the velocity of the slider A. So the velocity of A is therefore 0.834 meter per second. So the direction is in that direction because obviously since B is moving in that direction, it will also pull, no? It will pull the slider towards the right because of its rotation. So the velocity of A is 0.834 meter per second. It's lesser than the velocity of B and the direction is towards the right. So the direction is known because it is a slider. So it will move horizontally only. So that is the velocity of A. The second unknown is the angular velocity of the connecting rod AB. So the angular velocity of this connecting rod AB or the connecting rod 3 or the link 3. So to get that, since we already know this relationship, we can actually use this relationship already because that is equals to this angular velocity. So this is the same. So the angular velocity of connecting rod AB is equals to these ratios here. So we can substitute any of the value we want to get the angular velocity of the connecting rod AB, which is 1.79 rad per second. So therefore, the angular velocity of this connecting rod is so much lesser as compared to the angular velocity of rotation of this crank. So later on in application, when it moves so fast, this link here will move slow, 10 times slower or 5 times slower, no? Around that compared to the crank. So that is how you can use, again, the Centro method to determine the velocity and the angular velocities of points. And then we have another example here. So we are given with, this is the same, no? The same problem, but we will use the another approach in solving the same problem. So to solve the same problem, first you are going to compute for the velocity of B. We're using the formula 2 pi n. And then 2 pi n multiplied by the length of the link AB. So that's 2 pi n r or 2 pi n AB. Or that is just equals to W or omega AB. And draw the equivalent length on the point B. So we draw the equivalent length using the velocity scale at point B. And since we know that it's moving in clockwise, so the direction would be here, and it's perpendicular to the AB. So that's the velocity of B. And then you locate the IC that includes the link BC. So you locate since B is connected to this link, so we can use that IC. So that is the IC. So we locate the IC. So this is the IC that includes the link BC. So you can see that in the image. And then from the IC, draw a circle with a radius equal to ICB. So you draw that circle equal to ICB. And then we transfer the length VB to the length CD, perpendicular to CD that intersect with the generated circle. So we swing it to the link CD, connecting the instant center to C. So that is the equivalent VB. And then we draw a line from the terminal of VB in link CD to the IC. So that is the line we connect. And then in that line, we determine the magnitude of C by drawing a line perpendicular to CD and intersecting with the line from the step 5. As you can see here, this line, this BC is perpendicular to CD. So the velocity of C is perpendicular to CD because it's its axis of rotation. And the intersection of this line to this terminal line would be the absolute velocity of C. So this is just similar to the instantaneous center method, which is method number 2. So as you can see, we can still get the same result. Say for example, you know the point Q, you know the distances, and what you wanted to get is you wanted to get the angular velocity of BC. So to get the angular velocity of BC, you can use the formula. Angular velocity of BC is equals to the velocity of point P and the distance Q to B also is equals to the velocity of C divided by the distance QC. So that is how you can get the angular velocity of this floating link using this method. As you can see, it's similar to the method number 2 actually. It's the same also for the second problem. So you can compute first for the velocity of B using the formula 2 pi n r, no? That's 2 pi n r or 2 pi n or the omega multiplied by the radius of gyration. And then you draw it, knowing that the direction of the rotation is in this direction clockwise, then it will move in that direction here, perpendicular to this OB. And then you locate the IC that includes AB. So that is the IC. So it includes the link AB. So it should include the the link that you wanted to get the angular velocity. So since we wanted to get the angular velocity of crank AB, so we need to get the IC that includes, so not just all the IC, the random IC, but the IC that includes the link of concern. And then you draw a circle with radius equal to ICB. So that is a circle. And then similarly, we swing that VB, transfer that VB to the line ICA. So as you can see here, that intersect with the generated circle. So that's a VB, and then we draw a line from the terminal of VB in line AC to the IC. So this is the line, it will intersect the terminal of VB. And then, since we know that the direction of A is in this horizontal line, then we determine the magnitude of A by drawing a line along the path of A and intersecting with the line from the step B. So this is now the velocity of A, which is the same result that we get previously. So whichever approach is easier for you, you can use that method. So in the previous method, we will use trigonometry to get first the length. But in this method, we no longer have to use that. We just use the graphical approach. So we are able to verify the Centro Method and Instantaneous Center Method can be combined actually in solving different problems, similar problems. So now that we are familiar with the 3 method, the last and final method, which is the relative velocity or the velocity polygon method. So the good thing about this method is that it can be applied to almost everything. So this is done by constructing a velocity polygon with absolute velocities that originate at the pole Q. So we use the pole Q. We will define that pole Q later. All lines in the velocity polygon are perpendicular to the corresponding letter links. So let's remember this statement that all lines in the velocity polygon are perpendicular to the corresponding links. The term here is the velocity polygon. So we will construct a velocity polygon, and the lines in that velocity polygon is perpendicular also to the actual links. Say for example, you have here a problem, you are given with a non-parallel equal crank mechanism, which is drawn to an original scale of 1 1/2 is equals to 1 feet. The crank Q2A is 9 inch. So Q2A, so this crank here, Q2A is 9 inch and is rotating. So this is the direction of rotation with a uniform angular velocity of 60 revolution per minute counterclockwise. So this crank is locating counterclockwise. The connecting rod AB is 3 feet and 4-inch long. So this AB here is 3 feet 4-inch long. And we determined the absolute instantaneous linear velocities of the slide D. So we wanted to get the linear velocity of this point D, the slider D, and the point P. So this point P here, located 1 feet from A, so AP is 1 feet, no, because it's 1 feet from A on this length AB, and the absolute instantaneous angular velocity of AB. So we also wanted to get the absolute instantaneous angular velocity of AB, or the omega AB, so the floating length AB. So this is kind of a complicated problem, but we can still use the method. We will use the velocity polygon method to get this unknown. So we are given with QTA, which is 9 inch, AB is 40 inch. The angular velocity of A is 60 RPM. And the unknown are the velocity of D, the velocity of P, and the angular velocity of AB. So again, we are going to first locate a pole Q. So we calculate first the velocity of A using the formula 2 pi nr, diba? So that's the formula, 2 pi nr. The 12 here and 60 are conversion factors because our given is inch. So we convert it to feet by dividing it by 12, and we convert it to second by dividing it by 60. So our result now would be in feet per second. So that's why we substitute Q to A and also N, which is 9 and 60 respectively. So the velocity of A is 4.71 feet per second. And next, we chose a velocity scale. So we chose the velocity scale 1 inch is equals to 5 feet per second. So that the choice actually is depending on the magnitude of the known velocities. As you can see here, it's close to 5 feet per second. So that's why if we will use this 1 inch 5 feet per second, then the length of the A would almost be 1 inch. So therefore, every 5 feet per second is 1 inch in the drawing. So that's what we mean by the velocity scale. So 1 inch in the drawing, 5 feet per second in actual. So therefore, since our 1 inch is 5 feet per second, therefore this 4.71 FPS is 0.94 inch in drawing, because if we use this kV, therefore we'll just multiply this by 1 over 5, right? So that's 4.71 divided by 5. So 4.71 divided by 5 is 0.94 inch. So the drawing now, in drawing, the velocity of A is 0.94 inch. So you locate the pole Q first, and then from Q you draw QA representing the velocity of A, which is perpendicular to the line Q to A and is 0.94 inches long. So how do we do that? So we will, from Q, we'll draw a line perpendicular to Q4B representing VB. So first we'll locate the pole Q. So the location of pole Q is actually depending on you. So pwede na siya bisag as long as it's convenient to measure and to draw the lines. So we just draw it closer to the different links. So the Q is located here. You can locate it again anywhere you want in the paper. So you locate the pole Q, and then from Q, draw a line QA representing the velocity of A. So this QA, since the velocity of A, since this is the line connecting Q to A, so this is the line Q to A, we will draw QA perpendicular to that line. As you can see here, this QA, the length of this QA is equals to 0.94 inch. So that is 0.94 inch, because that is the value of the velocity of A. So the Q to A is perpendicular to the line joining Q to A in the actual drawing. So as you can see, Q2 or QA is perpendicular to QA. So that's what we mean by drawing QA representing VA perpendicular to Q2A and is 0.94 inches long. Then from Q, you draw a line perpendicular to Q4B representing the velocity of B. So the Q4B line is this line. So that is the Q4B. We are going to draw um, from Q a line perpendicular to Q4B. So this is Q4B, and then the line perpendicular to a line from Q perpendicular to Q4B is this line. So as you can see, it is from Q and it is perpendicular to Q4B. And then we from A, you draw a line perpendicular to AB, representing the direction of VBA. So since this is our the velocity of B relative to A, so that is the velocity of B relative to A. So this QA now, so from A, this Q, this QA, draw a okay. So the first step is to calculate the velocity of A using the formula. The velocity of A is 2 pi, the radius of gyration of A, and the revolution per minute of A. So that is 2 pi Qn, 2 pi Rn. So the value here, 12, is a conversion factor from 12 to feet, from inch to 12, and then the 60 here is the conversion from minute to second, so that our result for the velocity of A will be in feet per second. So when you substitute the value of Q to A and N, we can get the velocity of A as 4.71 feet per second. Then we chose a velocity scale so that we can draw this velocity in our paper. So let us say that you chose 1 inch is equals to 5 feet per second. So the choice is actually what is convenient in drawing. So since 4.71 is close to 5, so we chose 1 inch in the paper is 5 feet per second in actual. So therefore, if we use this velocity scale in drawing, the velocity of A will be 0.94 inch, or that is simply 4.71 divided by 5. So 0.94 inch in the drawing can represent the velocity of A. The next step is to locate the pole Q. So the location of the pole Q is depending on where you wanted to place it, so that you can easily draw the perpendicular lines to the actual linkage. So that's why I place it near the different links so that we can easily draw the lines later on. So you can place it anywhere. So that's the location of pole Q, and then we draw Q from Q, from this pole Q, we draw QA representing the velocity of E perpendicular to Q to A and is 0.94 inches long. So it's 0.94 inches long because the velocity of A is 0.94 inch in the drawing, and that represents the velocity of A. So first, we draw the line Q to A, so that is Q to A, and from that line, we will draw perpendicular to that, because we all know that the velocity is perpendicular to the link. So we draw the Q2, the velocity of A perpendicular to that line, and that is 0.94 inches long. So we draw it 0.94 inches long. So that's why we have here QA. So that's the value of that is 0.94 inches long. So it doesn't have to intersect now because it is just it just has to be in perpendicular. So 0.94 inch. So this is 0.94 inch. So that now represents the velocity and the direction of A. And then from Q, draw a line perpendicular to Q4B representing the velocity of B. So point B is located here. So obviously point B will rotate perpendicular also to this axis of rotation because the axis of rotation of B is this Q4. So therefore, we will draw first Q4B. We draw that line. We extend that line. And then perpendicular to that line is the velocity of B. So we will draw a perpendicular from Q. So that is the line perpendicular to Q4B. And in that direction is the direction of our B. We do not know yet the magnitude. So to get the magnitude from A, we draw a line perpendicular to AB representing the direction of VBA. So we have this line AB here in the drawing. Then the AB should also be perpendicular to this line. So that's why we draw it here, as you can see. So this line here is perpendicular also to AB because the velocity polygon is just a mirror of the actual and they are perpendicular. So the AB in the velocity polygon is perpendicular to the AB in the actual linkage. So that's why it's perpendicular. And then we locate B at the intersection. So since the direction of B is in this line here, and the intersection would be the velocity of B. So the velocity of B is therefore the QB. And then we can get the VB, the velocity of B relative to A as AB. So this line here, this solid arrow is the velocity of B. And this is also the direction. So as you can see, its direction is perpendicular to this Q4B, this one. This is the magnitude already. And then this AB here is the velocity of B relative to A. So this dotted line. So this is the velocity of B relative to A. And it represents the velocity of this point B here relative to point A. And then from Q, you draw a line perpendicular to Q4C. So this is to get now the velocity of C. It represents the direction of C. So since C is perpendicular to Q4C, we will use that line. So we have this line, Q4C. And then from Q, you draw perpendicular to this Q4C. So we have it here, it's perpendicular. So this represents now the direction of C. So it's perpendicular to this line. Then from B, we draw a line perpendicular to BC, representing the VCB. So since this is again a mirror, we'll draw again a line here. And then perpendicular to that line from B is also the representation of VCB in the polygon. So we draw that perpendicular from B. So as you can see, this BC somewhere here would be the mirror of this BC here. So the intersection therefore is the point C. So the C is at the intersection. So this is now our point C. Therefore, the velocity of C is QC, and the velocity of B relative to C is the line BC. So this is our QC, represented by the solid line. So this should be until this intersection. And then this line here from B to C is the velocity of B relative to C. So this is the relative velocity. So B is a relative velocity because, as you can see, B here is relative to C. So they have relative velocity. So as you can see, they are just mirroring the actual linkage. So now we'll draw Q. From Q, we draw a line parallel to the path of travel of D, representing the velocity of D. So say that we have here since our D is constrained to move in this direction, the velocity should also be in this direction, parallel. No? So it's the parallel. So that is where the slider, it should be parallel. It represents another direction. Then we draw a line from C perpendicular to CD, representing the velocity of CD. So this is our CD. And then we draw a line from C perpendicular to that. So this is the line perpendicular to CD. So that is why we located our D at the intersection. So this is our velocity of D. So the velocity of D is the line QD here. So this now is our velocity of D, and then VCD is the velocity of D relative to C. So this line here connecting D and C is the relative velocity of D to C. And since this is the unknown, we wanted to get the velocity of D, the actual velocity. We will measure it using our ruler, this QD. So we know that the direction of D is downward also, because the direction in the velocity polygon is the representation of the actual, also in the drawing. So the velocity of D is, we can get that by measuring this line and we multiply it by the velocity scale, which is 5. So say that you measured it as 0.9 and then the velocity scale is 5. Therefore, our velocity of D is 4.5 feet per second. So that is how we use the velocity scale in getting the actual magnitude. So whether you use different kV, the result will still be the same. So this is now our complete velocity polygon. So you can see that it is really a representation of the linkages that you can see here in our drawing. You can see that our C and B, so they are connected to Q. So C and B is connected to Q. They form a triangle here, CBQ. And the line AB is also connected here. That's this AB. Then we also have a line CD. So this is the CD. They are connected. CD is also connected here. BC is connected. BC is connected here. AB is connected. AB is also connected here. Therefore, if we wanted to locate P, we locate P in the velocity polygon by making a ratio and proportion of the length AB and AB. So this link AB here and this link AB. So we can get P by doing a ratio and proportion. Somewhere here lies point P. So by ratio and proportion of these two lines, we can get AP at a distance of 0.249 inch from point A. So AP from A to P is 0.249 inch. So that's why we have it here, point P. So as you can see, it represents. So APB, so we also have APB in the actual drawing. So since the velocity of P is QP, then we can get the velocity of B, absolute velocity, by drawing a line, an arrow again from the pole to the point P. And then we measure that and multiply with the velocity scale to get the actual magnitude of the velocity at point P, which is the another unknown. So that's 4.7 feet per second. So as you can see here, all of these lines here that's connected directly to Q are the absolute velocities. So the absolute velocity of A is QA, absolute velocity of P is QP, absolute velocity of B is QB, absolute velocity of C is QC, and then we have QD. And all these broken lines are the relative velocities. So for the angular velocity of AB, we can use the formula. The angular velocity of AB is the velocity of B relative to A divided by the length of AB. So this is another unknown, right? So the velocity of ABA is the velocity AB in the drawing. So we measure this AB and we multiply it with the velocity scale and we divided it by the actual AB in the drawing. So if we do that, we can get the angular velocity of the link, the floating link AB, as 1.23 rad per second. So that is how you use the velocity polygon in getting the different unknowns of the different points, the velocities and angular velocities of the different points in the linkages. So if we're going to finalize our answer, this is how it would look like. The velocity of D is moving downward. The velocity of B is moving in that direction based on the polygon. And then these are the values that we get from the calculation. So it's important to summarize your final answer so that it will be easier also to check. So here are some optional video that you can watch if you wanted to know more about the resolution and composition method, instantaneous axis of velocity method, Centro method, and the relative velocity or velocity polygon method.